Welcome to the Introduction to Forces video. This is the first video to get you started on Unit 3, which is forces that are balanced. So we're going to start here rather than with some notes. What we're actually going to do is we're going to start here with a little video. This video is from Scholastic's Study Jam, so you can watch it again if you would like to.
Okay, Sam, let's practice that kick of yours. Show me what you got.
Here goes nothing.
Okay. If you're gonna reach the goal, you're gonna need a lot more force than that.
It's not force I need, Mia. It's skills. I'm just not so great at soccer.
Sam, skills aren't gonna do you any good if the ball doesn't move. And if you want motion, you need force. Watch.
Now that's what I call a kick.
Thanks. What it really is force. A force is any push or pull on an object.
And your kick was quite the push.
Definitely. Before, the ball was just sitting there, waiting to be moved. The force of my kick sent the ball into motion. The crazy thing is, if my kick was the only force pushing on the ball, then it would just keep on moving. It would never stop.
That's impossible.
No, it's not. It's inertia, the tendency of an object to resist change in its motion. Inertia is what kept the ball still before I kicked it, and keeps it moving once a force is applied. Once something starts moving, inertia will just keep it going.
But what if that was like a bowling ball you just kicked? Bet inertia couldn't move it so far.
Well, a bowling ball would have barely even moved with the tiny amount of energy you kicked with. It's got a lot more mass than a soccer ball, and objects with more mass respond more slowly to force because their mass actually increases their inertia.
So that means it's harder to move things with a lot of mass and harder to stop them, right?
Exactly. But once you get those masses moving, inertia takes right over and keeps things rolling, just like the soccer ball. Well, unless...
Unless I stink as bad at kicking bowling balls as I do soccer balls?
No, unless another force is applied to it, like gravity pulling it down, or friction. Friction is a force that acts against moving objects.
Is that what made my ball stop?
Well, that's part of it, yeah. Friction acts between surfaces that touch. The friction that stopped the ball was caused by the bumpy, rough texture of the grass. The force of friction fought against the force of the kick.
And it looks like friction won against your kick, too.
Looks like you're right. That ball's done rolling for now.
Definitely. So then how do we beat the force of friction and get the ball to keep moving?
Well, the more friction there is...
Oh, the more force you need to apply?
Exactly. Or more newtons.
Fig Newtons.
No, Sam. A newton is a measure of force.
Ah,
Anyway, you were right. Greater force equals a greater change in movement. And the more force you want, the more energy you'll need.
of course.
Aha! Now you say of course, but when you kicked that ball earlier, I didn't see you put much energy into it.
Well, I had no idea I was fighting a battle against friction. Now I know just what it takes.
Not so fast. Sometimes, friction's not the only thing you're fighting against. Gravity is another force that can work against motion.
Whew. Friction, mass, gravity. No wonder this soccer business is so hard. That's like a whole team against one rolling ball.
Well, you just gotta come to the field in full force, Sam. Ready to give it one more shot?
Well, if you're talking about the basics of force, I think I've got that down. A force is a push, like a kick, or a pull that acts on an object. We need force to set objects into motion, and the greater an object's mass, the more force that's required to move it. Force not only moves things, it stops them too. Friction is a force that acts against motion and can stop an object in its tracks.
But not this time. Go for the goal, Sam.
Oops, guess I'm quite the force to be reckoned with now.
Okay, so let's take a look at some of that information from that video and let's talk about it and take some notes about it so that you have a better understanding of how to represent those forces. I'm not going to write the definition of force down again. I think you got that. It's a push or a pull. But a couple of types of forces were mentioned in this video that we need to discuss. So we have contact forces, and we have long-range forces. As you can imagine, contact forces are forces on a system that is because of contact. So these are forces due to things touching. For example, right now, you're probably sitting on something or another, and so you are touching the object that you're sitting on. Say you're sitting in a chair. And so that chair and you are applying contact forces to each other. The other type of forces are long-range forces. Long-range forces result because objects are inside a force field of some sort. So these are forces due to interactions with fields. Due to interactions with fields. Now, by a field, you often think of like Star Wars, the Force be with you, that sort of thing. But what we're talking about with a field here, in this particular case, is things that we can actually measure. Things like magnetic fields, or electric fields, or gravitational fields. Now, in terms of what we're talking about, actually, I'm going to add one more in here as well. Another one is nuclear fields. We don't often think of nuclear forces as being long range because the nucleus is so small, but as we'll see next semester when we really get into some chemistry, there's a lot of space between the objects that are applying forces to each other there. When we talk about contact forces are the ones that we're most familiar with. Contact forces are, for example, the push that they mentioned in the video, or a pull, or friction was also mentioned. Now, for about half the time in this unit, we're going to ignore friction. The other half the time, we're going to use friction, and I will make sure that it's clear whether you need to include it or not. There's also tension. So if you pull a spring or if you compress a spring, then we have tension that we need to deal with, which is also a contact force. We also have what we call the normal force. A normal force is the force between an object and the surface it is in contact with. This symbol here means perpendicular, and I'll come back to normal forces in a little bit, but I want to mention them here. We also have, we have drag force, which is sometimes considered friction, but it's not always considered friction because it's in a fluid. So we also have drag. And we have the buoyant force. Buoyant force is what allows you to float in water, or a balloon to float in air. So we have these forces. We have to figure out how they compare to each other, how they interact with each other, and most importantly, we have to be able to describe them and show them in what we call a force diagram. So, for example, if we think about the most basic set of forces that we can, we want to draw a force diagram. We're going to keep them simple for the moment. We'll get more complicated in a little bit. But let's say that I have a table. And on that table, I have a box. Okay. If I want to draw a force diagram on this, I have to first of all know what forces exist. Well, first of all, we have a force that is the weight of the object pulling it downward. We sometimes don't call it the weight of the object. We don't call it FW. Oftentimes we will say that, well, weight is due to gravity. So really it's the force of gravity pulling down on it. And I want to clarify this over here because this is super important. So F of W, which is how I would write the force due to the weight, we often write as F of G, which is the force of gravity. Now here on Earth, gravity is 9.8 meters per second squared. We're going to round it for the moment. And we're going to say that gravity is 10 newtons of force, or 10 meters per second squared. And what that means then is if I know that the mass of this box is 1 kilogram, then the weight, or the force of gravity, force due to gravity, is the mass times the gravitational force. And so the weight of this object is 1 times 10, which is 10 newtons. Okay, so this here, that weight is mass times gravity, is an important concept to keep in mind. So we've got our gravitational force coming down on here. At the same time, we have this normal force that I mentioned up here. So when the box pushes down on the table is going to push back up on the box. And we call that a normal force. The normal force is perpendicular to the surface of the table. Okay? And so the normal force is the table pushing back up. Oh, I forgot the A. Now, this is a force diagram per se. It shows that there are two forces acting on this box. If the box is just sitting there and it's not going anywhere, it doesn't have any other forces. Also, if the box is sitting there, then these forces must be equal because they aren't moving. I don't like to always have to draw all of the whole setup and all of that out. So when we draw a force diagram, what we do is we transfer the object that we're interested to into being a point source. So for our force diagrams, while you can start out drawing them like this, what we really want to get to the habit of is saying, I want to show all the forces on my box. So I'm going to draw my box as if it's a point. And then I'm going to say, okay, well, I have the weight going down. And I have the normal force going up. Because it's not moving, they are the same. So I put hash marks on them just like I would in math to show that they are congruent with each other. This is probably the most simple situation that we can draw for a force diagram. Let's get into a little bit more complicated one here. And let's see if we can look at one that has more than just two forces acting on it. So let's assume that I still have my table. And I still have my box. But this time I have a string attached to my box, which goes over a pulley. Oops, and is attached to a series of weights. Okay? And when I let go of the string and I let go of the weights over here that are hanging, this box is going to move in this direction. Okay? And at this moment, then we have a lot more stuff going on. So if we look at the forces on this object, we still have the force of gravity. We still have the normal force. But now we have a force pulling it this way, which we will call the force of tension, Ft. And because it's on a surface, and we didn't say that it was ice, we also have force of friction. So we have the normal force, we have weight. These are equal to each other because it's not moving up or down, so we know these forces must be equal to each other. Before I put enough weight over here, before I put enough hanging masses over here, there's still tension in the rope, but this may not have yet started. Okay, so we have our F of F, which is equal to the force of friction. And we have F of T, which is the tension in the rope. Before it moves, F of F is equal to F of T. And we can see that because I've drawn the arrow lengths almost to be the same size. But once it moves, once I put enough weight on here, let's say I add another mass, couple of masses here, then my force of tension is going to get greater, and my force of friction is not. So now, when it moves, let's assume it's moving at a constant speed. So when it moves at a constant speed, the force of friction is going to be less than the force of tension because it's moving. So there has to be a force pushing it in order for it to move. So when we are thinking about this situation and we want to draw a force diagram for this particular situation, we want to simplify it some. I don't want to have to draw all of this stuff out. I want to have to look at just one object again. So I am going to create my system. My system is going to be just the box. So I'm going to focus on just the box. Because if I focus on just the box, then I can shrink my box to a point and I can just have my forces on it. So if I focus on the box, then here's my box. I know I have gravity. I know I have the normal force. It's not moving up or down, so I know those are equal. Then I know I have a tension force. And I know I have a smaller force of friction. Okay? At this point in time, with these two forces not being equal, this is what's going to happen when it just starts moving. So sorry, let me change this up here. When this starts moving, starts to move. So this is when it is starting to move. Once this box starts moving and it has overcome its initial inertia not to move, then the tension force isn't going to increase anymore, but the frictional force may increase again because of kinetic friction, because of moving friction. And when it does that, then my force diagram is going to change ever so slightly again. I still have my gravitational force, I still have my normal force, those are still equal, but now my force of friction and my tension are also going to be equal if it's moving at a constant speed. So when it starts moving, it accelerates from 0 to some speed, and this first force diagram is what you have. When it's moving at a constant speed, this second diagram is what you have. So how do you do this? How do you keep this in mind? What is this talking about? Well, let me simplify this and put it on the next page. So in order to analyze your forces in a diagram, to draw a force diagram, a few things you want to keep track of. Number one, you do actually want to do a sketch of the system and its surroundings. So in other words, you want to draw the whole table, the box, the rope, and the pulley there. The second thing you want to do, though, is you want to draw a dotted line or I think I did a solid line in the last one, but around what I want to consider my system. So I drew my entire system and the environment here with the table, the box, the pulley, the weights. And then I drew a yellow, orange box around just the box on the table, just this part here, because that's the only thing that I really want to think about. Third step is to shrink the system to a point that is located at the center of the object. And you want to make sure that your point and your axes that you're thinking about are the axes that include your gravity, your normal force, and the potential directions of motion that the object's going to go in. The fourth thing that you're going to do is you are going to draw the force vectors. The force vectors are the arrows. With labels and relative sizes. So in other words, like we did here, I made the box a point. I said the normal force and the gravitational force are the same, so I tried to make the arrows the same. To double check that the arrows were the same, to really let you know that, I put the hash marks, the congruency hash marks on them. To show that the friction was less than the tension, I made the arrows smaller. And I labeled all of the arrows with the force of whatever it is. And then once it got going to constant speed, I made another force diagram showing that the tension and the friction were the same. And again, other set of congruency marks. Now, keep in mind that when you're doing this, you want to make sure that you can easily separate your forces into X forces and Y forces, the objects that are working in the X direction and the objects that are working in the Y direction, because those are the ones that are going to make it easier for you to analyze in the future. So let's draw one more here, and then I think you've got it. Let's say that we've got a boat hanging out in the water, okay? If the boat is just sitting there, then we know that we have a gravitational force because of its weight. We also know that it's not sinking, so there has to be a normal force on it. There has to be a force that's pushing it back up from the water. Because it's water, we don't actually call it a normal force, though. We call it the buoyant force. And if the buoyant force and the gravitational force are the same, then that means that the boat is not flying up out of the water, nor is it sinking down into the water. If the buoyant force were more than the weight of it, it would go flying up out of the water, which would be a little bit weird. If the gravitational force were greater than the buoyant force, then it would be sinking. Okay, so because it's just sitting here, we know that those two forces are going to be the same. If it's not going anywhere, then that must mean that the water is not moving. So this could be in a pond rather than in a river or an ocean. So when we make this is not a true force diagram because it has the object in it. When we make this into a true force diagram, you put a dot, you put buoyant force going up, you put gravity going down. And that's it. You're done. Hopefully this explains force diagrams. They're a pretty basic concept. Just keep in mind the sizes and the directions are important, and to label your forces. This is what assignment 3.1 is about, and you're just going to be drawing the diagrams. If there's not enough space on Desmos for you to change it into a dot, then just go ahead and do what I've done here on the boat and put your forces right on the boat, the cat, the giraffe, whatever the pictures are on the assignment. We will talk more about this and get more into forces in greater detail on Tuesday at class. Bye for now.